Look at the sky. Go on. On a clear day, step outside and look up. You see the sun. You feel its warmth pressing against your skin. You are certain, absolutely certain, that you are experiencing something real, something solid, something that simply is. I want you to hold that certainty for just a moment, because by the time we are finished today, I am going to show you that what you believe you saw, what you believe the sun is, has never once been the full story. You have been looking at a shadow of a deeper reality. And the science that reveals this is not speculation. It is not philosophy. It is the most confirmed, most tested, most precise body of knowledge human beings have ever assembled. It is quantum mechanics. And it begins perhaps with me. My name is Louis de Broglie. I was born in 1892 into a family of French aristocracy, but it was not the halls of nobility that shaped my life. It was the strange and violent collision of two ideas that nobody in the early years of the 20th century could reconcile. The question of what light actually is. And I can tell you now, from where I stand, that question does not have a simple answer. It never did. Let me take you back. For centuries, two great minds stood on opposite sides of a debate about the nature of light. Isaac Newton, the towering figure of classical physics, argued that light was made of particles, tiny corpuscles he called them, traveling in straight lines, bouncing off surfaces, being like miniature cannonballs fired from the sun. On the other side stood Christian Huygens, who insisted that light was a wave, a ripple spreading outward through space, capable of bending, interfering, and diffracting around obstacles the way water ripples bend around the edge of a stone. For over 200 years, these two camps argued, and for most of that time, the wave theory seemed to be winning. By the late 19th century, the experimental evidence for light as a wave was so overwhelming that the matter appeared settled. Young's double-slit experiment had shown that when you send light through two narrow slits, it does not create two bright lines on the opposite wall the way two streams of particles would. Instead, it creates a beautiful pattern of alternating bright and dark bands. The signature of interference, the unmistakable calling card of waves overlapping and either reinforcing or cancelling each other. Waves one, case closed, or so everyone believed. Then came Max Planck. In the year 1900, Planck was wrestling with a problem involving black body radiation, the way objects glow when heated. The predictions of classical wave theory gave results that were catastrophically wrong at short wavelengths, producing what physicists came to call the ultraviolet catastrophe. Planck solved the problem, but at a cost that disturbed even him. He found that the mathematics only worked if he assumed that energy is not continuous, not a smooth flow like water, but is instead emitted and absorbed in discrete packets. He called these packets quanta. The energy of each packet, he showed, is equal to a constant, his constant h multiplied by the frequency of the radiation. E equals hν, a formula so small in its writing, so enormous in its consequences. Planck himself hoped this was merely a mathematical trick, a convenient tool that would eventually be explained away. Then, in 1905, a young patent clerk in Bern named Albert Einstein did something far more radical. He took Planck's quanta seriously. Einstein proposed that light does not merely interact with matter in discrete chunks. Light itself is discrete chunks. He proposed that light travels through space as individual particles of energy, which we now call photons. Each photon carries energy proportional to its frequency. High-frequency light, violet, ultraviolet, carries high-energy photons. Low-frequency light, red, infrared, carries low-energy photons. With this single idea, Einstein explained the photoelectric effect, the curious phenomenon where shining light on a metal surface can eject electrons from it, but only if the frequency of the light is above a certain threshold, regardless of how intense the light is. The intensity of light adds more photons, but only frequency, only the energy per photon, determines whether those electrons are knocked free. Einstein was awarded the Nobel Prize for this work, and rightly so. But now physicists had a crisis on their hands. Because he here was light, already proven beyond doubt to be a wave by interference experiments, and now proven equally beyond doubt to be a particle by the photoelectric effect. How can the same thing be both? How can the same beam of sunlight landing on your face be simultaneously a spreading ripple in a field and a stream of discrete energy bullets? This was the question that consumed the best minds of the early 20th century, and it was the question that consumed me. I was studying for my doctorate in Paris, working under the influence of my brother Maurice, who had himself been deeply involved in studying X-rays, another form of electromagnetic radiation that displayed the same baffling duality, being having as waves in diffraction experiments and as particles in other measurements. I had come to physics rather late, having first studied history, and perhaps it was that outsider's perspective, that freedom from too many ingrained assumptions, that allowed me to ask a question that in retrospect seems almost obvious, but which nobody had thought to ask before. Einstein had shown that light, which everyone knew to be a wave, also behaves as a particle. So I asked, what if the reverse is also true? What if particles, things that everyone knows to be particles like electrons, also behave as waves? The symmetry of this idea is what they mean. Nature tends towards symmetry. If wave-like light can behave as a particle, then particle-like matter should be able to behave as a wave. I proposed in my doctoral thesis of 1924 that any moving object, any particle with mass and momentum, has an associated wavelength. I called these matter waves, and I gave the precise mathematical relationship. The wavelength is equal to Planck's constant divided by the momentum of the particle. Lambda equals h divided by p. A simple formula, a profound formula. Now, I want you to understand what this means, because this is where the sun becomes strange. The light arriving at your eyes from the sun right now is not simply a stream of photons traveling in straight lines. Each photon has a wavelength. Each photon has a frequency. Each photon carries a precise quantum of energy. But and this is the point that changes everything, that photon, between its moment of emission deep inside the sun's core and its moment of detection by your retina, does not travel as a particle at all. It propagates as a wave of probability, a wave that spreads, diffracts, interferes with itself, explores multiple paths simultaneously, only when it is detected, only when it interacts with your eye or a detector or any physical system, does it resolve into a definite location, a definite event, a definite photon. Before that moment of detection, asking where the photon is not a question with an answer. The photon is not somewhere. It is a wave of possibility spread across space. Let me be more precise, because I do not wish to be mysterious for the sake of mystery. The wave I am describing is not a wave of something physical in the classical sense, not a wave of water or sound or even electromagnetic field in the old way of thinking. It is a wave whose mathematical square at any given point tells you the probability of finding the particle at that point if you make a measurement. Max Born gave us this interpretation, and it has never once been wrong. The wave function, that is the name Schrodinger gave to the mathematical description of this wave after he built his famous equation on the foundations I laid. The wave function is the most complete description of a physical system that quantum mechanics allows, and what it describes is not certain. It is potential. It is probability. It is the ghost of what might be, waiting to become what is at the moment of observation. Now let us return to the sun. When a hydrogen atom in the core of the sun undergoes nuclear fusion, when 4 hydrogen nuclei fuse into 1 helium nucleus, energy is released in the form of a gamma-ray photon. That photon begins a journey. It bounces and scatters and is absorbed and re-emitted countless times as it travels outward through the dense solar interior. This process takes, on average, somewhere between 10,000 and 100,000 years. The energy that warms your face today was generated in the sun's core long before modern human civilization began. But here is what I want you to hold in your mind. At every step of that journey, the photon, this quantum of light, is not a tiny ball traveling in a straight line. It is a wave. It is a smeared out probability. When it finally escapes the sun's surface and travels the 150 million kilometers to Earth, it is propagating as a wave function, exploring all possible paths, interfering with itself, carrying within it a kind of deep indeterminism that is not a deficiency of our knowledge, but a feature of reality itself. What you see when you look at the sun is the result of trillions upon trillions of these quantum events. Photons being emitted, traveling as waves, colliding with the molecules in your eye, being absorbed by rhodopsin molecules in your retina, triggering electrochemical signals that travel to your brain and are interpreted as vision. Each one of those absorption events is a quantum event. Each one is at its core a matter of probability. The color you perceive, the intensity you experience, these are the statistical result of an inconceivable number of quantum happenings. You have never seen the sun. You have seen the quantum echo of the sun, filtered through the probability amplitudes of photons and the electrochemistry of your nervous system. And now, and this is where I want to go further because the implications reach beyond light, consider that your eye itself, the instrument doing the seeing, is made of matter, electrons, protons, neutrons, atoms bound together in molecules, and every one of those particles, every electron, every proton, also has a de Broglie wavelength. The electrons in the atoms of your retina are not orbiting the nucleus in neat little circles like planets around a star, the way Bohr first imagined and textbooks still sometimes show. They exist as standing waves, patterns of probability wrapped around the nucleus in shapes determined by the solutions to Schrodinger's equation. When my matter wave hypothesis was published, Niels Bohr's model of the atom already gave the right energy levels for hydrogen, but nobody could explain why only certain orbits were allowed. My answer was simple. Only those orbits are stable in which the electron wave fits perfectly around the nucleus, where the wave closes smoothly on itself after each revolution, like a snake biting its own tail with no gap and no overlap. Orbits that do not satisfy this condition produce destructive interference. The electron wave cancels itself out. The orbit does not exist. This was not merely a better way of calculating. This was a revelation about what matters. Matter is not made of tiny solid balls. Matter is made of waves, waves of probability, waves that can interfere and diffract and tunnel through barriers that classical particles could never penetrate. Quantum tunneling, the ability of a particle's wave to leak through a barrier that the particle classically lacks the energy to cross, is not a strange exception. It is a routine feature of the quantum world. And it is relevant to the sun once more. The process of nuclear fusion in the sun's core absolutely requires quantum tunneling. The temperature at the sun's core, as high as 15 million degrees Celsius, is actually not hot enough for protons to overcome their mutual electrical repulsion through sheer kinetic energy alone. Classical physics says the sun should not be able to fuse hydrogen at all at these temperatures. The sun should not exist, or at least should not shine. But it does because protons are quantum mechanical objects with de Broglie wavelengths, and their waves can tunnel through the Coulomb barrier with a small but finite probability. Enough tunneling events per second across the vast number of protons in the solar core sustain the fusion reactions that power the sun. The sun shines because matter is a wave. The sun shines because of quantum mechanics. The sun shines because of what I discovered in 1924. I want to dwell on this for a moment because I think it is one of the most extraordinary facts in all of science, and it is not nearly appreciated enough. Every ray of sunlight that has ever touched this planet, every photon that drove the photosynthesis that created the oxygen you breathe, every quantum of warmth that allowed liquid water to persist on Earth's surface and allowed life to emerge and evolve, all of it traces back to quantum tunneling. All of it traces back to the wave nature of matter. When you look at the sun, you are looking at the most spectacular ongoing demonstration of quantum mechanics in the solar system. Now, I am aware that some of you may find this troubling. You may feel that I am describing a universe that is somehow less real than the one you thought you inhabited. If the sun is a quantum object, if the photons are waves of probability, if the matter in your eye resolves into standing probability amplitudes, does anything actually exist? Is there a real sun at all? This is a question I spent much of my life thinking about, and I will be honest with you, it is still debated. The interpretation of quantum mechanics, what it ultimately means about the nature of reality, is genuinely unsettled among physicists. The Copenhagen interpretation, associated mainly with Niels Bohr and Werner Heisenberg, says that asking what the photon is doing before it is measured is a meaningless question. Physics describes what we can measure, not what is. I was never fully satisfied with this answer. I proposed what I called the pilot wave theory, the idea that particles are real definite objects, but they are guided by a real wave that propagates through space and steers them. In my picture, the photon is both a wave and a particle, the wave always existing, the particle always having a definite position, but the wave determining the probability of where we find it. David Bohm later developed this interpretation into a complete theory, and it remains a viable alternative to Copenhagen today. There is also the many worlds interpretation, in which every quantum event branches reality into multiple parallel outcomes. Each of these interpretations is consistent with the experimental predictions of quantum mechanics. We cannot yet distinguish between them by experiment. What I can tell you, what no serious physicist disputes, is the mathematics, the predictions, the extraordinary, almost incomprehensible precision with which quantum mechanics describes the world. Quantum electrodynamics, the quantum theory of light and matter, predicts the magnetic moment of the electron to better than 1 part in a billion. An experiment confirms it to that same level of precision. No theory in the history of human knowledge has been tested so stringently and found so accurate. Whatever quantum mechanics means philosophically, it works. It works to a degree that staggers the imagination. And so, when I tell you that you have never seen the real sun, I am not speaking loosely. The sun you see is a constructed experience, a neural interpretation of quantum events, filtered through an instrument, your visual system, that is itself made of quantum objects having according to quantum laws. The photons arriving at your eye are the collapsed remnants of wave functions that have been propagating for 8 minutes through space. They carry information about a surface that is itself the result of trillions of years of quantum mechanical processes. The nuclear reactions in the core, the radiative transport of energy through the solar interior, the convective cells boiling at the surface, the emission of photons from the photosphere, every single one of these processes is fundamentally quantum mechanical in nature. The sun you see is real. I am not saying it is an illusion, but it is not the complete story. It is the shadow cast by a deeper reality, a quantum reality that is richer, stranger, and in many ways more beautiful than the classical picture of a bright burning ball of gas. The real sun is a quantum furnace, powered by matter waves tunneling through barriers of force, radiating probability packets that we call photons, which then propagate across space as waves until they resolve into events in detectors and eyes and instruments. That is the real sun, and it is more magnificent than anything Newton's classical universe could have contained. I want to leave you with one final thought. In 1927, 3 years after I published my doctoral thesis, Clinton Davison and Lester Germer, working at Bell Laboratories in the United States, performed an experiment in which they fired a beam of electrons at a crystal of nickel. The electrons scattered off the crystal and produced a diffraction pattern, exactly the kind of interference pattern that only waves produce. My prediction was confirmed. Matter behaves as waves. The wave nature of the electron was real. Davison and Germer had no intention of confirming my theory when they began their experiment. They stumbled onto the result almost accidentally. But the universe does not care about our intentions. It behaves as it is, and what it is, at its foundation, is quantum mechanics. In 1929, I received the Nobel Prize in Physics for my discovery of the wave nature of the electron. The first person to receive the prize solely on the basis of a doctoral thesis. I am told this is unusual, but what I want you to remember is not the prize. What I want you to remember is the idea that the boundary between waves and particles, the boundary that Newton's universe drew so firmly, that the textbooks of the 19th century treated as absolute, is not a real boundary at all. It is a boundary drawn by our limitations, not by nature. Nature, at its deepest level, does not distinguish between wave and particle. Nature speaks only in wave functions and probability amplitudes and quantum states. And every beam of sunlight that falls on you is nature speaking in that language, whether you have the tools to hear it or not. You have never seen the real sun, but now perhaps you are a little closer to understanding what it actually is.